I'm going to review a little bit of multiplication of our basis unit vectors, look at how they behave in terms of a dot product and then a vector cross product. So the notation that we have for our unit vectors, if I sketch out a little coordinate triad to indicate the three positive directions for our coordinates. Z is along k hat, x is along I hat, and y is along j hat. And I'm drawing it out this way with like some indication of implied perspective here to do a three-dimensional image. I'm doing it this way because it's a right-handed coordinate system. And so for a right-handed coordinate system, a rotation that takes the x-axis into the y-axis is a positive rotation about the z-axis. And a positive rotation is one that is counterclockwise when viewed from above. It's a convention used in physics. All right, so the dot product with our unit vectors is pretty straightforward because the dot product as a mathematical operation is asking how much of a vector points along the direction of another vector. And well, no part of x points along y, no part of y points along z, so this is fairly straightforward. And they are unit vectors, so I hat dot I hat is 1. I hat dot j hat has to be 0 because no part of x points along y. I hat dot k hat is also 0. No part of x points along z. And then we can go through and fill these in for the other possibilities. And the dot product commutes, so I'm sort of doing more work than I need to do, but I'm trying to be complete. No part of y points along x, all of y points along y, and it's a unit vector, so their dot product is 1. J hat dot k hat is 0. No part of z points along x. No part of z points along y, and z is parallel to itself and it's a unit vector. So that's what we have for the dot product of unit vectors. The vector cross product, and the cross product is meant to tell you a vector direction that is perpendicular to the two other vectors. So the way the cross product is going to work out, to say in words before I write out this little tableau of values, is that the cross product of a vector with itself has to vanish because the vector is parallel to itself. And then for these unit vectors, like j and k are perpendicular to each other, so we have to go through and find whether it is going to point along x or minus x. Those are basically our two choices. You get like a bit further along into mathematics, there's a better way to do this in terms of something called the Levi-Civita symbol, which is a totally anisymmetric tensor. But we're not using tensors in this class, so instead, when it comes to figuring out what the cross product of unit vectors are, you can just come back, look at this tableau, or reason through yourself whether it's a right-handed or a left-handed rotation. I have to tell you whether it's plus or minus. We'll go ahead and fill this in. I hat cross I hat has to vanish because there is no unique direction perpendicular to those two vectors because they're the same vector. I hat cross j hat is k hat, positive. I hat cross k hat is minus j hat. So x cross z is minus y. j hat cross I hat is minus k hat. So if I reverse the order, x cross y is z, y cross x is minus z. Okay? J hat cross j hat has to vanish. There is no unique perpendicular direction. Then we have j hat cross k hat is I hat. So y cross z is x. K hat cross I hat is j hat. And k hat cross j hat equals minus I hat. And then k hat cross k hat has to vanish. So for the cross product of the unit vectors, these are the 9 possibilities, and you see that they are in pairs. Along the diagonal you've got 0, and then the pairs off diagonal, x cross y is z, but y cross x is minus z, I cross z is minus y, but z cross x is y. We have y cross z is x, and x cross y is minus x. And remember that the order for a vector cross product in general, if a cross b is equal to c, if I reverse these, b cross a is minus c. Okay, so the vector cross product does not commute. The order matters, and that comes down to whether it is basically a positive or a negative rotation. Going back to our original discussion. So when you need to go back to break down vector multiplication operations in terms of what do the unit vectors do, you can come back to this, and it's also in your book. Under the dot product, it's fairly straightforward that a unit vector is parallel to itself, and it's a unit vector, so they're normalized. And then for vector cross product, the cross product of a vector with itself has to vanish because there's no unique direction that's perpendicular. And then we have our rules for whether it is basically going to give you a positive or a negative value.